Hi everyone, I'm Ankit. I completed my master's in scientific computing and I worked in industry in various roles as a data scientist, product manager, and a software developer. Throughout this journey, my core focus has always been to help people accelerate their data analytics and scientific computing pipeline. And today I'll be talking about Numba, which is one such tool which can help you supercharge your code in Python. To begin with, we researchers love Python because it is easy to learn, the codes written are usable and readable, it has a vast ecosystem of more than 250,000 plus contributed packages. It takes fewer lines of code to implement new algorithms and build prototypes and scale them. A feature-rich Jupyter Notebook ecosystem allows us to have an interactive environment where we can write our codes, mathematical equations, display visualizations, and add narrative texts. This even promotes reproducible research and scientific transparency. And the list goes on and on. But when I was pursuing my master's 6 years back, working on transport phenomena, solving multiple differential equations, I was hit very hard by the fact that when it comes to performance, Python implementation was magnitudes slower when compared to traditional languages like Fortran and C++, which made me question if learning Python is so easy, why is increasing the performance of my Python code so difficult? Thankfully, times have changed. A lot of effort has been made in the last decade and two to accelerate Python. You can have a look at some of the alternative implementations and packages which aid acceleration in this need for speed timeline. Broadly, there are two ways to speed up your Python codes. One is by using a replacement Python interpreter like PyPy, which is difficult to implement, which has its own ecosystem of Python packages, which is significantly smaller and limited. The other popular alternative is to use Python to C++ transpilers like Nuitka, Python, and Cython. They have limited static analysis and ahead of time generated code is either bloated or under specialized. Also, both these alternatives do not address non-CPU targets like GPUs, which are gaining widespread adoption in the scientific computing community. And then there is one library, Numba, which stands out in this crowd. It is easy to learn, use, and implement just like learning Python. And it often provides performance gains comparable to traditional programming languages. As there is no ahead of time compilation step, so using it is straightforward and you can directly plug it in into your Jupyter Notebook environment. So what is Numba? It is an open source JIT compiler which translates a subset of Python and NumPy code into fast machine code. All you need to do is add a JIT decorator to your Python function and you will gain performance similar to C, C++ and Fortran without switching languages or interpreters. To understand how Numba works, we can quickly go through the process which happens behind the scene. So first, you add the ngit decorator to the function you want to accelerate. Ngit stands for JIT in no Python mode, which is the preferred mode to supercharge your code as there is zero involvement of the Python interpreter in the compiled code and this leads to the best performance. When the function is invoked for the first time in the session, a bytecode analysis of the Python function is performed based on which a Numba intermediate representation is generated. The function arguments are also analyzed to infer the data types, post which the IR is rewritten. This high-level and abstract Numba IR goes through the process of lowering, which converts it into low-level and machine-specific LLVM IR. Based on the CPU or GPU target, the LLVM or NVVM compiler infrastructure is used to generate optimized machine code, which is executed. If you pass cache equal to true option, then it will persist the compiled code on your disk, which can be used across sessions. So let's get started with our first example. We will compute the Mandelbrot set, a set of points on the complex plane which always remains bounded by a threshold value, while solving the quadratic recurrence equation. It is an iterative problem which is also very compute intensive in nature. The first step is to import the requisite libraries, which we will be using throughout this exercise. Next, we will set up the domain size as a 500 cross 500 grid and limit the maximum iteration for each point on the grid to 1000. Now let us write a pure Python function to evaluate the Mandelbrot set and return a nested list of color tuples for the entire domain. Since we are using only Python, we will use the data structures available natively. We will initialize a nested list of tuples denoting the color of each pixel on the complex plane. Next, we will traverse the complex plane using nested for loops. Here, y denotes the index along the imaginary axis and x denotes the index along the real axis. The complex number corresponding to each grid point is initialized and we begin the iterative computation. When C breaches the threshold value after a certain number of iterations, the corresponding color tuple is evaluated using a mathematical function. Finally, the function returns the color of the entire grid. Let us now execute the function. You can see it took around 7 seconds to execute the entire function. We can visualize the generated Mandelbrot set using the Python ImageLink library. It looks fascinating. Now let us see if we can speed up the entire computation using Numba. All we need to do is create a copy of the above function and add the Numba JIT decorator. Let us execute the function. Wow, it took less than a second. Now let us execute it again. The performance improved even further. Since we did not provide any specification regarding the function input types in the ngJIT decorator, Numba does a lazy compilation of the function. When the function is executed for the first time, it does the type inferencing and compiles the code which is directly used for all successive execution. We test the results and yeah, it looks good. So we got an enormous performance boost just by applying the ngJIT decorator. But is that it? No. Numba also provides you with certain options that can enhance the performance even further. All you need to do is switch the parallel option to true and Numba will generate codes capable of parallel execution on multiple threads. In this case, we will also specify the for loop we want to execute in parallel using the prange function available in Numba. So I have parallelized the loop execution along the y-axis. So let us now execute the function. Amazing, it took less than 100 milliseconds this time. You can clearly see the improvement in performance is even further. So you can inspect the default number of threads that are being used by Numba using the Numba num threads config variable. In my case, it is 16. And you can also set the number of threads which can be used by Numba using the set num threads function. Let us set the number of threads as 4 and execute it. Some other options available in the ngJIT decorator are fastmath and cache. Fastmath reduces the numerical rigor, which can help you gain further improvement in performance. Also, you can persist the compiled code on disk, which can help you avoid the overhead you experience in the first run. Now let us move to the next example, where we will use NumPy array as the data structure. You can see the code logic is exactly the same as we had in the pure Python version. If you are new to NumPy, you are not familiar with vectorization and array expressions, you will tend to use for loops to access and modify arrays. In this function, I am doing the same. Now let me execute the function. You can witness the function is not up to the mark as accessing NumPy arrays using for loops is quite expensive. Let us see if Numba comes to our rescue. We once again create a copy of the function and add the ng decorator. After executing the function, we can see that the performance gain is quite significant and slightly better than what we achieved using the pure Python code. Now, let us switch the parallel option to true and add the prange function and execute it. This time, the performance gain is quite significant because though NumPy is primarily designed to be high performant on single core, Numba automatically compiles a version which can run in parallel if it contains reduction functions, array math functions, and many more functions, assignments, and operations. If you are well versed in NumPy universal functions and vectorization, Numba can still help you speed up your scientific computing pipeline, as it allows you to write ufuncs in Python instead of C and directly compiling into NumPy ufunc. There is a NumPy counterpart vectorized decorator which vectorizes a Python function, but it is just for simplicity and it is neither optimized nor efficient. So let us first start with the NumPy vectorized decorated function. You can witness its performance is slightly better than the nested for loops. Once we switch to the Numba vectorized decorator, we are able to compile it into a ufunc which performs significantly better. To add icing to the cake, you can also create a ufunc which can execute in parallel using the target option, which increases the performance even further as we can see here. Moving to the final example, we will solve the diffusion equation where a steel square block is at an initial temperature of 300 Kelvin and it is subjected to 700 Kelvin boundary temperature. We will solve the differential equations using central difference method in space and forward difference method in time. We will set up the domain, provide the initial conditions and define the thermal properties. The number of time steps we will undertake is 500 and the U0 specifies the temperature field at time t equal to 0. Using for loops, we have a readable code. Now let us go ahead and execute the function. It takes around 12 seconds to execute. We can plot the temperature field and inspect it. Now, let us rewrite the function using NumPy vectorized expression. This totally eliminates the need for loops. After executing the code, we are able to obtain 200 times faster performance. But the sacrifice is huge in terms of code readability. The more complex the equation, the more difficulty we will have in understanding the code. Number provides a stencil decorator which comes to our rescue. A stencil is a computational pattern which automatically generates the looping code required for a neighborhood. It allows clearer, more concise, and high performance code. We start by defining a kernel which computes the equation we want to apply on the domain and add the stencil decorator. In case the kernel is not applicable on the boundaries, the output value of the boundaries defaults to 0. This can be changed via cval parameter as we have specified in this case, which is thot or 700 Kelvin. Now let us go ahead and execute the code. The performance gain is more than 700 times, which clearly demonstrates how you can supercharge your scientific computing code using Numba without hampering the code readability. To summarize, it is a good idea to use Numba for numerical algorithms which are array oriented, math heavy, have lot of loops. When the data is in the form of numpy arrays, when the performance bottleneck is a handful of well encapsulated functions. You can use Numba to create universal functions in Python that can be broadcasted over numpy arrays instead of writing them using C APIs. You can also use Numba to generate parallel codes targeting multi-core CPUs and GPUs. And as we have already seen, you can create fast and clean codes using the stencil kernels. Now let us check out a real-life open source project which has benefited from Numba acceleration. The name of the project is blurhash Numba, which is the fastest Python 3 blurhash implementation. So blurhash is actually quite popular and used in popular sites such as Reddit, Medium as a placeholder while the network image is still loading. So blurhash algorithm takes an image and gives a short string which is only 20 to 30 characters that represents the placeholder for this image. So the process of encoding is basically conversion of an image into a blurhash string, and the process of decoding is the conversion of this blurhash string into a blurred image. As compared to pure Python implementation, in blurhash Numba, there was a speed up of around 33 to 63 times while encoding an image, with sizes ranging from 128 x 128 pixels to 2048 x 2048 pixels. Also, the process of decoding saw a performance boost of 34 to 70 times for the same target image sizes. Such performance gains can have a tremendous financial impact and help you save money when you are running image processing algorithms like blurhash on serverless frameworks where you are built based on the function usage, which mostly includes the runtime. In case you are already using Dask or Rapids, Numba integrates with them seamlessly. Also, you can install Numba using Berryconda on Raspberry Pi and speed up edge device computation, for example machine learning scoring or any other edge device analytical computation. With this, we have come to an end to this talk. If you have any questions, please feel free to ask me in the Q&A session. You can find the notebooks used in this talk on my website, which is realworldpython.guide. So thank you for attending this talk and have a nice day.